Okay, well this thing is not just that, but it's pre-multiplied by h, which means it's being mapped into observation space. So this is nothing other than the estimate of the observations in the prior again, those YEs that I mentioned previously, normalized by the observation error covariance. Okay, well, if you're following the story up until now, the next step is perhaps the most important. We do a singular value decomposition on that operator. And so singular value decomposition gives us three things. It gives us a left singular vector matrix and a right singular vector matrix and a diagonal matrix of singular values. And then we're going to use these matrices, U, V, and lambda, U and V in particular, to change coordinates again. We are now going to map to a hat space by projecting the tilde variables using these right singular vectors. So essentially, these are linear combinations of the state to this new set, all right, using these singular vectors. And we have another map for the observations using the left singular vectors. And this is the analogous quantity where we are taking a linear combination of the measurements. So we're trading the measurements for a linear combination of the measurements. Nothing gained, nothing lost. We're just shifting the basis. We're rotating, stretching, however you want to think about a linear transformation. And if you plug that into this equation, you get the following, which again looks almost exactly like the Kalman filter update equation. We have the analysis in the hat state is equal to the prior in the hat state plus weighted, gain-weighted contribution from the innovation in this space. Now this is really amazing. This is what the gain matrix looks like in this space. The problem has been completely diagonalized now. So lambda is a diagonal matrix which has the singular values, and therefore the gain matrix in this space is now diagonalized. Okay? And the way the singular value decomposition works is that these singular values are rank ordered. So they are greater than 0 and greater than or equal to 0, and they're rank ordered, right? So they go from the biggest one to the smallest one. And then there are vectors that are pairs on the left singular vectors and the right singular vectors that go along with each one of those singular values. Okay, so this is pretty special. By symmetry, we note that where we usually find the observation operator on the prior and the innovation, we again find the singular value matrix. So we can think about that as the observation operator in this purely diagonal space. Yeah, okay, so the other thing, if we do this in an ensemble space, which is where I'm going to actually evaluate it, is we've crunched this problem down as small as we can make it. It's been crunched down to everything that contributes information, which is the number of observations by the number of ensemble members. That is all the information we have. If we want to get more information into this analysis, we either have to get more observations or we have to bring in more ensemble members. So it's another way of looking at this is that we've crunched this down to the smallest space where there's no longer any redundancy. So it's purely diagonal. Okay, if we take another step, we can rewrite the analysis in a somewhat similar fashion to what Eugenia talked about yesterday, is that we have kind of a weighted version where these two pieces of information are weighted. We have identity weighting on the background, and then we have a weighting of the observations by the singular values. So what this is going to tell us is that some of these are going to be really important and others are going to be less important. And again, it's linear combinations of the observations. Yeah, I see what you're saying. It looks like this lambda should be hitting this lambda. Okay, so maybe don't trust this line here. There may be some typesetting problems here, maybe even a problem in my notes. But I'm pretty confident in that one, and I'm pretty much positive in that one. Yeah. So for that last millennium reanalysis that I talked about this morning, this is what the singular value spectrum for that curly H looks like. So we have 539 proxies for the experiment that I showed you this morning, which means we have 539 linear combinations that we're replacing those measurements with. And the singular value spectrum is very, very steep. So there's a subspace here which contains most of the information. Right? So this is the analog of averaging. We're adding together in a special way all these measurements, and that is what's covariating most strongly with averages of the state together. So it goes all the way back to that superob concept I talked earlier, but it's much more general than that. And then we have this long tail that will add incrementally small bits of information, but not nearly as much in any one degree of freedom than those first 10 or 20 do. And here's an example. So I picked one particular year, and I did the reconstruction, the full reconstruction, with all 538 of the proxies. Okay, and these are the temperature anomalies that apply to that year relative to the baseline, which is 1960 to 1990. All right, so we see it looks like it was a La Nina year when we have these temperature patterns around the world. So this is the same reconstruction, but only using the first singular value and the first singular vector pair that goes with it. So you can think of this as that special average of all the proxy data and the pattern that we can reconstruct with it. And perhaps not surprisingly, it's giving us something that's large scale, right? So these large scale patterns are the most robust, especially around the continents and in the Pacific Ocean. So this is apparently for this year the most robust spatial pattern that we can reconstruct. Then if we do the same analysis with 10 singular vectors, so again, we're just going back, we're going back to this. We're saying we're going to use 1, and then we're going to use 10, we're going to use more and more. If we do 10, you can already see it's, it's doing better than this. Now it's starting to get some of the details. It's got the idea of this La Nina state. So with only 10 singular vectors, we're able to recover a lot of the solution that we have with everything. If we randomly picked 10 proxies and did a reconstruction, we get nothing similar to this. Right? It's this special linear combination that has all the information. Here's a reconstruction with 100. So that's not even 20% of the data, and it's already getting pretty close to the solution. We're already starting to get out into the tail of that singular value spectrum.
It's strange that the number 1 is completely different from all the rest.
Well, so the way I interpret this is that it's a lot like that coupled data assimilation problem I talked about this morning. But the averaging starts to tell you about things that are longer and bigger in space. So the global mean is probably one of the more robust things that we can reconstruct. You could just think about if we averaged all the proxies, weighting them by their error, then that's kind of a global spatial average, and that should be the thing that covaries best with the global mean. So I think there's a lot of global mean signature in this.
Could it be that the sign is wrong?
If the sign was wrong here, then the sign will be wrong for all of these. Yes, sir?
Is it mathematically rigorous, and that way the first value is the mean, or that it's...
That's a qualitative interpretation. The mathematical, like the quantitative answer is what's shown there. That picking that first singular value, it plucks off those 2 singular vectors on the right and the left. And this is the analysis that you get from just that 1 degree of freedom. And I'm interpreting this as, well, in part because Chris and I started out on this to try and understand why averaging seems to work so well, and if there's a generic framework where averaging fits in. Right? Averaging is a very simple thing to do, But there are more flexible ways or more general ways of doing that that perhaps may give us deeper insight. And this was our attempt at doing that. So maybe I was anticipating this. That was my expectation, that the largest scales, the thing that average across the most of the proxies, the more averaging we do, we know the more noise we're going to take out, that it should touch on something that's global. Maybe I'm wrong, but that's the way I'm interpreting it. Any other interpretations? Okay. Yeah.
If you do localization in a practical implementation, that would kill you, right? Because that takes out exactly that aspect.
You have hit the nail on the head, Sebastian, on two things. One is that localization is problematic for the global mean. So we have done solvers where we take the global mean out and treat it as a parameter in the augmented state and then localize the departures from the global mean. Well, we use really long localization length scales compared to what we're used to using in weather problems, because on these annual time scales, the correlation length scales are really long. So when we're using correlation length scales for ensembles of size 200 of around 25,000 kilometers, we're not losing very much of the global mean. So that's matter number one. Matter number two is there is no localization in what I've done here. That is definitely on the to-do list. But because it's not serial observation processing, it's all at once, it has to be done at the B matrix level, which means it's going to blow up B, and we're going to lose our little space. It's an excellent point. And so this is the first step on the path in that direction.
Is it just a coincidence that the first value gave almost in all the points on the map a positive value?
It could be particular to the year I've chosen. So I've just plucked off 1 year for purposes of illustration. I haven't done any, rigorous comparison over a long period of time. Yes, you can imagine, well, especially once you get out of the 20th century, and this is from some year in the 1950s, I believe. Yeah, so certainly if we go back to the Little Ice Age, we would probably expect this map to be blue. But I'm guessing that the main signature is still going to be large scale. It's not going to be small scale details. And just a reminder again, just so I can keep track of time. What time is this lecture supposed to end?
2.
At 2, okay, good. I think we'll actually end early. Okay, so now when we're in this optimal space, we can do the same thing that we did before with the Cardinale approach. So the recap is, this is the special matrix that we do the SVD on. This is just a summary of what I talked about before. And then we could talk about the impact of the proxies in this space, doing the same thing, except we're taking the derivative of the estimated proxies in the posterior in this transform space with respect to the transform measurements in that space. And this is what it looks like. And then we can get back to the original space by back transforming using that matrix which maps between the proxies in the original space, the measurement space, and the special hat space. And again, it's ordered by the size of these singular values.